Hey, good afternoon, everyone. Welcome to the latest seminar for the U.S. Society for Ecological Economics. I'm John Palomeni, the current president, and today we have a interesting paper presentation from Veronica Lupi. She's an assistant professor at the Department of Environmental Economics in Rye University. Hopefully that's close enough. And she's also a senior researcher at Eni Enrico Mattei Foundation in Milan. She has some very interesting work that she does on climate change and population dynamics, and that is one of the things that we'll be hearing about today. So with that, I'll turn it over to Veronica, and thank you very much.
Thanks a lot for this nice introduction, and good afternoon, everybody. So today, the title of my seminar will be Climate Policies, Population Dynamics, and the Urban-Rural Contribution to the Social Cost of Carbon. And the outline of my presentation will be as follows. First, I will give you a bit of introduction to this topic. Then I will show you some hopefully nice and interesting preliminary results related to my current research, basically, which connect population dynamics, climate change economics, and also rural-urban dynamics. And then, of course, we will draw some conclusion. The overarching question of my work could be the following. As global population changes and as we know, cities, urban agglomerates expand, how these forces shape the social cost of carbon and potentially climate policies. Just to give you a very quick definition, just to remind that the social cost of carbon reflects the marginal damages or costs of the consequences of climate change, or you can see it as the societal cost of each additional ton of CO2 emission. The social cost of carbon is a measure that has been used, at least in the past, we will see in the future, has been used to set the optimal level of the carbon tax, the so-called carbon price, because basically the social cost of carbon is the optimal carbon price that internalize the climate change externality. So from the environmental economic point of view, that's where, marginal benefits equal marginal cost. And there, given the fact that climate change is inducing some kind of damages, we can compute the optimal social cost of carbon or the optimal carbon tax. To be more specific, in what I will show you during this presentation, we will look at how population dynamics and urban-rural dynamics contribute to the social cost of carbon. And basically, what I will show you is related to these two papers, working papers that you see here, because that's not published research yet. The first one is more on population dynamics, let's say, and my co-authors are mainly from University of Pisa and University of Milan, while the second work is with some colleagues from Vrije University, the Environmental Economic Department in the Netherlands, and also a colleague from Mexico, which is a climate scientist. And you will see that in that case, the model we will use, it's a bit more complex. What is interesting, I believe, is that integrating all these dimensions might provide some possibly equitable and effective climate policy. That's a step forward, I would say. But, I hope I will walk you through what I have in mind with this type of research. Very quickly, just to give you the idea in which framework we are moving. So usually I work with integrated assessment models. So very criticized models, macroeconomic models that link the economy and climate in a very stylized way. You can see here, as I said, a stylized representation of what an integrated assessment model is. Basically, you have an economic module and a climate module. Within 15, 20 equations, you can describe the economic dynamics. And basically from the economic dynamic, the society produces emissions. Those emissions affect the climate module through the carbon cycle, where basically is described within a few equations how emissions accumulate in the atmosphere and how then these cumulative emissions affect climate dynamics through temperature, basically. And then you have the feedback to the economy, because through the damage function, which again is a very sensible module within integrated assessment model, basically we can convert how climate change affects the economy in terms of GDP loss. Now we move to the first part of this presentation. This is something that is quite well known in not only in the economic community, but in general to the environmental community, let's say. That's this one that you can see in this equation one is the IPAT equation. That's an accounting equation where basically on the left-hand side, I represents the environmental impacts. Usually in my framework, the environmental impact is proxied by CO2 emissions. On the right-hand side, you have the main drivers of the environmental impact that are population, affluence, proxied by GDP per capita, and technological innovation. Of course, as I said, this is just an accounting equation, but luckily for us, there is also a stochastic version that allows to estimate the so-called ecological elasticities. So basically here in equation 2, you can see the operationalized version of the IPAT equation. And what are these ecological elasticities? Basically, ecological elasticities refer to the sensitivity of environmental impact, I, to a change in any of the driving force. As you can see again, impact, as I will show you in my case, in my framework, is represented by CO2 emission. And then, of course, you have population, affluence, technology, and you have B, C, D. Those are the so-called ecological elasticity. To give you just an example for population elasticity, B, refers to a change in environmental impact, of course, a percentage change, due to a 1% change in population, holding the other drivers constant, of course. And what we do with this ecological elasticity, so basically we include the stirpat formulation within the most important and, well, the most famous, let's say, integrated assessment model, which is the dynamic integrated model of climate and economy. That's the DICE model. And we allow these drivers, and mainly focusing on population, to be independent, let's say, to be independent drivers of emission, because of course, changing the ecological elasticity, the value of ecological elasticity, the drivers of environmental impact could be more or less important in terms of how they affect the CO2 emissions in our case. The model setup is very simple because basically it's a global model. It's a Ramsey type framework. So basically it's a welfare maximizing model where we consider the social planner equilibrium, and the social planner takes into account both the economic constraint and the climate constraint, let's say. No international trade, industrial emissions come from production activity, as I told you before. Technological change is exogenous, and we have a stylized carbon cycle and temperature dynamics. Stating all this setup, it's also already possible to see what are the limitations behind this work. But let me move on, and in case I will tell you more on this later on. I will not show all the equations of the model, no point in that, because I would like to focus more on the result. In case you have question, I can answer to that later on. But just to give you the feeling, I mean, our modification is quite easy because basically what we do is look at equation 4. That's the equation that in the original DICE model described the evolution of emission. E stands for emission. And on the right-hand side, you have a parameter sigma, which describes the energy efficiency dynamic of the economy. Then you have this mu t, that's a control variable, an endogenous variable within the model, a very important one because that represents the abatement level for each point in time. And then you have Q, which is gross production, okay? And in equation 3, basically you see how we modified such equation in order to include the ecological elasticities. So N represents population, and then of course Q over N, that's GDP per capita. In this way, we included population and affluence, basically. On the left-hand side, we have I, the environmental impact, which is emissions, as I told you before, and that's sigma here represents in some way technological innovation. Phi and psi, those are the ecological elasticity. In order to choose the value for these ecological elasticities, we refer to the extensive empirical literature, which through the years tried to estimate such numbers, the value of such numbers. And then what we do is we test for several configurations of the ecological elasticities what happens within the dynamic of the DICE model, of our integrated assessment model. Let me tell you that with regard the affluence or the GDP per capita, the ecological elasticity referring to GDP per capita, so psi, there is quite some consensus in the econometric literature saying that this psi is less than 1, while the main problematic part, of course, is for the ecological elasticities for population, because some papers says that this pi is greater than 1, others says that this pi is equal to 1. As you can see, basically, if you look at 3 and 4, if phi and psi are set equal to 1, of course, we are back to the original equation in DICE. While if we, of course, change the value of phi and psi, then we can include this stirred dynamic within our model. In the configuration, in the result I will find you later on, we took the value for these ecological elasticities less than 1 for psi and greater than 1 for phi, so for population. And that, of course, already probably tells you that, of course, we will see something different compared to the original DICE model. Of course, when you work with integrated assessment model, you work also with scenarios. And in our case, the scenarios that we consider are the following. Of course, a baseline scenario, which assumes no changes with respect to 2015, 2020 climate policy. So the hypothesis that climate policy will stay as it is until the end of the century. Then you have an optimal scenario or a cost-effective scenario, which identifies the optimal path of emission, balancing damages and cost, benefit and cost. That's the, let's say, the preferred equilibrium for environmental economists. And probably you also know that, and I can anticipate this, and that's the case in the original DICE model, in the optimal scenario, so the scenario in which we balance cost and benefit of climate policy, almost never emissions reach zero, because zero emission usually is not cost effective within our economy. While, of course, you can add additional, let's say, constraints, additional target, then you are not anymore in what we call optimal or cost-effective scenario. And for example, we consider the temperature scenario, where basically temperature is constrained such that by the end of the century, it cannot exceed 2 degrees with respect to pre-industrial era. Since a few weeks ago, our configuration for this scenario was constraining temperature up to 1.5 by the end of the century. But yeah, now we know that probably we are already overshooting that target. So yeah, now I'm using 2 degrees as a target for the end of the century, hopefully. And here you can see some preliminary results. Let me explain a bit the figure. So basically here you see 3 key variables of our model. On the left-hand side, starting on the left-hand side, you see emissions. In the middle, you have temperature, and then you have on the right-hand side, carbon price. I didn't call the last box social cost of carbon, because to be true to the real definition of what a social cost of carbon is, only for the optimal scenario, the carbon price that you see is equal to the social cost of carbon. Because, of course, in the baseline, it's another story, but in the temperature scenario, where we have an additional constraint on temperature, that's not what we call the social cost of carbon. The social cost of carbon is described usually by the optimal scenario, but that's just a matter of definition. Anyway, basically the dotted lines in all these boxes represents the original dynamics of the DICE model, while the solid lines describe the new, so to speak, results, including the ecological elasticities. We can concentrate on the description of the green lines because, for the sake of time. So basically, if we start from emissions on the left-hand side, so the dotted line describes the behavior of emission in the original DICE model. And as I told you before, you can see that, of course, the black lines represent the baseline, so where we don't abate further. So the green dotted line, of course, prescribes lower emissions compared to the baseline, because it's optimal to abate more. But as I said before, emissions do not reach zero by the end of the century. The solid grid line, instead, represents the result, including the ecological elasticities. So, as you can see here, basically, even in the optimal scenario now, emissions do reach zero. By 2070, emissions level is equal to zero, and stick to that result. Of course, you can see you can look at these dynamics also, considering the other variables, because if you look at temperature, basically, again, just focusing on the green lines, in the original DICE model, so the green dot line, basically, as a result of the fact that emission never go to zero, temperature is a bit lower compared to the baseline scenario, but still, by the end of the century, we are around 3 degrees with respect to pre-industrial level. While in the In our modified framework, including ecological elasticities, you can see that temperature reaches it's a bit above 2 degrees, let's say, but still a quite better outcome. If we look at the carbon price, and as I said, if we look at the green lines, we can talk about the social cost of carbon. In the original DICE model, in the original model without ecological elasticities, of course, as a result of the chosen path of abatement, the social cost of carbon or the optimal tax, let's say, by the end, it's increasing in general through time and reaches, well, it's a bit below $200 per ton of emission by the end of the century. You can see instead that in the framework with ecological elasticity, the social cost of carbon is a way higher, of course, as a result, because, and I mean, everything is coherent. By 2070, emissions go to zero. And as a matter of fact, by 2070, the carbon price or social cost of carbon has its own peak around $400 and then start going down. Why? Well, because now after 2070, emission flow, so the flow of emission will be equal to zero. It does not mean that damages will not be there anymore, because of course, the emission that accumulated in the atmosphere are still there. But of course, the level of the social cost of carbon or optimal carbon price start going down. The DICE model runs well beyond the end of the century, but of course, I mean, showing results after the end of the century with that tool, it's not really reliable in my opinion. So that's why usually I show just by the end of the century. Of course, offering several scenarios. Just for curiosity, the emission abatement, that's the mu t, the mu that we saw in the previous equation, the control variable of the model. Here, basically, again, just focus on the optimal case. The blue numbers represent the abatement dynamics within the DICE model. So by 2030, we should abate emission by 20%, up to 75%. Of course, as we saw before, we never abate 100% percentage in the original DICE model, while, of course, in our framework with ecological elasticities, the timing of abatement is quite higher compared to the original model. And as we saw in the figures before, by 2070, the abatement should be equal to 100%. So no more, no new emission within the system. Of course, very briefly, we tested for several configurations of the ecological elasticities. We also analyzed a bit pollution, the impact of pollution on preferences. We also consider different social welfare functions because, of course, when we talk about population dynamics, that's quite a tricky topic. And in particular, working with welfare functions, it depends on how population is considered in the welfare function. But yeah, that's in the paper. I don't want to spend too much time on this. And just to let you know. So it seems that given all the limitations, indeed accounting for population, but in general for drivers, including ecological elasticities, seems quite important because the timing of abatement changes quite a lot. Of course, in terms of social cost of carbon, we see that including ecological elasticities increase by 4 times the optimal level of the social cost carbon. And of course, as I anticipated, there are also some limitations because that relies a lot on the magnitude of the ecological elasticities, in particular for population. And this is a global model. Would be nice to have ecological elasticities that are regionally specific. So an integrated assessment model which is regional and not global in order to better capture even the various dynamics, especially in terms of population. But that's the preliminary, let's say, result that I have so far. And now, having said that, I'd like to move to the second part of this presentation. Bit different, but still in some way linked topic with what I told you before, because population dynamics could be used in several ways. And I will show you now how, in which sense it's connected to urban and rural, urban, non-urban impact, let's say, of climate change. So originally, of course, I'm Italian. I come from Milan. And so I will use this map of the city of Milan to introduce the second part of my presentation. So this picture represents land temperatures around Milan during the 18th of June in 2022. And that was a period in which Milan, we had a very bad heat wave, okay? So it's, of course, the temperatures were crazy. And you can see that in the surrounding of the cities, the areas are quite red, but some areas are more red than others, of course. And I can tell you that here on the corner, on the right-hand corner here, you have a very red area. That's the central station in Milan. While there are other parts of the city which are less red, and we can imagine that are less red, so the temperature, the local temperature is lower because there is some kind of vegetation probably there. And for example, here, this Sempione Park, that's a very big park. And in that area, there are a lot of trees in the, even in the street surrounding the area. And also this portion of the map here, that's the vertical garden. So the building, the two buildings with all the trees on it, quite famous. And the point why I'm telling you this, because basically we can observe that it's not only the heat wave per se, but within the city, there is also a local effect on temperature, especially in some of these areas in the city. And there is also another dimension, which I'm not really including directly at the moment, but it's quite interesting, I believe, is that the area of where the central station is, which is quite red, it's also one of the poorest area in Milan, while, as you can imagine, the area where the vertical garden project is one of the richest area. So there is also this dimension of how damages due to climate are distributed, even with respect to the economic situation of people living within a vulnerable area. And also, and sorry, I was looking at the chat, but I did. Okay. Beside this, yeah. So basically, it's also this dimension of inequality, economic inequality, which in some way is connected with how damages due to climate change are distributed. Moreover, what will be important for us in the last part of our presentation is this interaction with global effect of climate change and a local effect of temperature, of course, especially during maybe a heat wave. But I can tell you that, I mean, during summer in the latest year in Milan, it's like always being within a heat wave. So that's not only related to a particular moment in summer. The role of cities where it's not, I believe that that's quite clear, that cities account for, the top 100 city account for 18% of the global carbon footprint, and about 60–80% of global population will live in cities in current, if we consider current projections. And cities produce close to 80% of global GDP. So that means that within cities, big cities, the industrial, it's where the industrial production concentrates. And what's happening within cities is that, of course, the presence of buildings, the presence of industrial production, and also the density of population, because, of course, people want to move to cities because there are better opportunities from the economic point of view. All these situation factors are leading to the so-called urban heat island effect. The urban heat island effect alters local climate and is even expected to amplify economic losses from global climate change. Moreover, there is some literature that is saying that the urban heat island effect poses high risk for public health, for example, especially for low-income and marginalized community. So what we do in this second work, we include the urban heat island effect in ClimRisk, which is another integrated assessment model, but this time this model is spatially explicit. And we estimate the climate damages for urban and non-urban or rural areas. And that's quite important in terms of measuring the contribution of these areas to the social cost of carbon. Very briefly, the model results are at the grid level and can be aggregated in 187 countries, as well could be aggregating in 13 world regions. And also, of course, you can compute the global aggregate at this point. As before, climate change reduces economic output via damage function. And what we do, the damage functions are downscaled to the grid cell level, to the urban and rural areas are indeed identified, and also local climate change is included, so the urban heat island effect. We follow some papers that, help us in collecting the estimates that are needed in order to compute the country level and regional damage function. Urban areas are identified with two methods: using urban population projection and using population count with different thresholds, let's say. And how we check we are doing everything well? We need to reproduce observed and projected estimates of global urban population and GDP. Urban damage functions combine the country level and regional damage estimate, including local damage function that include the urban heat island effect. The model basically projects the intensity of the urban heat island effect using this equation here, which POP stands for population. So you can already understand that population here is used in another way with respect to the previous the previous work, but still it's quite important in order to understand the dynamics of urban areas, and also to see how to include how the urban heat island effect could be more or less dangerous, so to speak. This is a visualization of the model, but for the sake of time, let me move to the main results, basically, I want to show you today. So let me explain the figure. So here you see different histograms. These histograms represent 13 regions because the results have been aggregated on the basis of these 13 regions. Here you see US, Europe, Japan, Russia, and so on. And this is a bit based on how the regional version of the DICE model looks like, okay? So, because also, I mean, every time, the DICE model, Nordhaus models are very criticized in the literature, but then, of course, if you want to introduce something new, you, at least in the environmental econ literature, you almost always are required to compare to Nordhaus model. But anyway, that's just a curiosity. What do you see? Let's take the first histogram, that's US. So for the US, for the United States. So basically, with the dark blue field, that's the contribution to the social cost of carbon of non-urban areas. The orange field, that consider the urban area, but without any effect. Because the point is not only including the urban Italian effect, but being in the city per se worsen the situation and so also the climate damage for the people living in it. But this this orange field just consider the fact that, okay, that's the urban area without any effect. That's why urban and non-urban are contributing the same, it seems, because basically the further contribution of urban area is given by the green field. That's called urban exposure. And this urban exposure does not include yet the effect of the interaction between local global climate. And you can already see that the contribution of urban exposure, it's already quite important with respect to the total value of the social cost of carbon. And finally, the light blue field, that's the contribution of the urban Italian effect. So the fact that we have a local impact of climate change plus the interaction with global climate change. Basically, the contribution, if you look at all the 13 histograms, this last one represents the world, so the global social cost of carbon, but the trend is similar anyway. So the contribution of non-urban areas is quite small in terms of the social cost of carbon. It's about 7% even at the global level, and usually weight less than 10% in most regions. Then, of course, there is some variety, as you can see. And let's have a look because you can see that the let's say the light blue part, which is the contribution to the social cost of carbon to including the local effect of climate change, so the urban Italian effect, that gives the majority of the contribution to that measure. So if we consider the global social cost of carbon in our model, the global social cost of carbon would be around $460 per ton of CO2 emitted. And basically, 62% of this value is due to this interaction with local global climate. Of course, I have to admit something because we perform a lot of sensitivity analysis and we consider several scenarios, SSPS, so socioeconomic pathways. We considered also different discount rates because probably you know, the point is also how we do discount the damages due to climate change. And the result I showed here are produced using let's say, the most dramatic, the SSP5, which is the most dramatic set of projections with respect to population dynamic, GDP, and so on. Usually, we believe that currently we are in the middle of the road. So that the scenario we used here is too drastic, let's say. However, given the current socio-political situation and so on, I mean, probably we will never touch this point, but it's interesting, I believe, to have in mind such result. What I want to say is that using more less pessimistic, let's say, SSPS, of course, the magnitude of the social cost of carbon at the country level, at the regional level, and at the global level is a bit lower. But qualitatively, the relevance of the urban areas and the relevance of this effect of local climate change remains the same, okay? But we indeed perform quite a lot of this sensitivity analysis. And I'm close to the conclusion because basically we see that the social cost of carbon, the value of the social cost of carbon is influenced by a complex interplay of factors, including population, of course, GDP growth, urbanization, but also local warming. Our decomposition of the social cost of carbon into urban and non-urban area reveals that urban impacts indeed dominate, both globally and regionally. And we also see that cities are those with higher economic losses potentially from climate change. And that's true in both less advanced and advanced economies. So those are the main takeaways, I believe, at the moment. So probably population is indeed a crucial driver and influence emission quite a lot, but it's important to understand how to include this driver and to evaluate its effect. And urbanization amplifies climate costs, and probably that means that we do require localized policies to mitigate the global local interaction of climate warming. And our result, of course, especially in the first part of this presentation, suggests that increasing abatement effort is needed in order to keep up with tight climate targets. That's quite common result in this type of literature. And if ecological elasticities could be useful, it would be better, of course, to explore the regional heterogeneity of this ecological elasticity in order to better include the dynamics of the main driver of our environmental impact, in our case, emission dynamics. So it's interesting this fact that urban areas are indeed the place where maybe some climate policies should aim at, because within the city, even the inequality issue do matters, especially if we take into account this local global warming, because the poorest, the most vulnerable people are also penalized within the city itself. And what I'm interested in at the moment is also the connection with climate change damages and inequality measures, because I believe that's quite important topic at the moment. And with that, I'm concluding my presentation. So I hope I am on time. And if there are some questions, please, I would be happy to answer them.
Great, thank you. That was awesome and very interesting. A lot of very relevant information to what we're going through. So there's a question already. Alejandro, why don't you go ahead and ask your question?
Thanks, John. Thanks, Veronica, for your presentation. I just was wondering, in your model, benevolent dictator determines environmental elasticities. I think you mentioned it, right? Is it possible to model these elasticities from a more granular perspective that takes into account the impact of agents like households or firms, enterprises on the environment? And what are the challenges to find data at this granular level, in your opinion?
Okay. Thanks a lot for this relevant question, indeed. So the answer is yes. Technically, analytically, it would be possible to consider, let's say, a decentralized equilibrium. So we can consider households and firms. Of course, analytically, that will be a bit more challenging because, yeah, probably it's not possible to solve the model. I mean, we will need, anyways, a software to solve, to find at least a local equilibrium in the model, but it's indeed possible, I would say. Regarding the data, well, of course, it depends on the granularity, because if I understand correctly, and you have in mind, yeah, like at the household level, at the firm level, that would be maybe a bit challenging, especially if we want indeed to model all the countries in the world. Because then, of course, if at least the idea is to then aggregate up to the regional level, at least that would be easier. But otherwise it would be quite challenging. But again, I think that, I mean, at the moment, there are a lot of data sets available. So maybe the issue is a bit more with less advanced economies. Usually with Africa, I know that it's quite challenging to find data. But yeah, probably, I mean, at least it could be a start to have the model in order to include regional ecological, well, firm level, household level ecological elasticities, and solve the model from a decentralized perspective. So not anymore from the social planner point of view. And then, yeah, of course, in order to find the data, that's maybe a bit more challenging, as I said. But yeah, that would be for sure a way to go in this topic.
Thanks for your response, Veronica.
We have another question. Hopefully I'm going to mispronounce this. I apologize. Hervé? Hervé?
Yes, thank you. It's Hervé. Hervé Bersegola. I'm a physicist working in France. Can you tell us more about how you describe energy efficiency? And you said it's the progress in technology. And but does it depend on the other parameters, for example, on population?
No. Okay. Yeah. Thanks a lot for the question, because, yeah, usually that's a quite tricky parameter. So the parameter is exogenous, meaning that there is an exogenous law which represents the fact that GDP at the global level relies less through time to fossil fuel. So given the fact that in the original configuration of the DICE model, technological innovation, again, is exogenous, that represents the fact that through time we expect to be less dependent on fossil fuels. But it's very abstract, I would say, because, I mean, in any case, that's not enough to stop, to let emission decrease if we consider just the baseline scenario, for example, no? Because in the baseline scenarios here, so the black line, okay, there is a bit of policy, but just, I don't know, abate emission by 3%. We have this sigma there, which potentially is decreasing the effect of industrial production in producing emission. But as you can see, yeah, emission may be stabilized by the end of the century. But yeah, that for sure another important parameter.
But for example, you haven't tried to include learning by doing in the way energy efficiency will decrease or increase.
Yeah, that's again a nice comment. So there are some papers that work more on this technological part. And for example, yeah, I mean, learning by doing or R&D investment are indeed included, because it's also true that the results I show will be much lower in their magnitude if we start including, for example, as you said, endogenous technological innovation. That for sure. So that's also another limitation. But there are some papers, some previous work that is focusing more on this. But usually population dynamics is left exogenous.
Okay, thank you. It was very interesting. Thank you.
Are there other questions or comments? I will go quickly. Follow up with that. Some of the research we've done with Jevons paradox, rebound effect, some people call. I mean, obviously, in our Jevons book that we published, we use the same model, the IPAT model, and population and energy efficiency have both increased energy consumption. So how would something like that, given what your last comment was, how would that look like in your situation? Because with the urbanization and the energy efficiency, really, the technological change really not having a major impact, actually the opposite impact. It looks like things would just explode.
Yeah. And yeah, thanks a lot also for this question, this comment. That's true. I mean, I cannot compute with the DICE model directly, I believe, energy consumption, but for sure, I mean, I could do something, I mean, in order to indirectly compute that. And that's true. I mean, here, basically, the exclusion or not inclusion of endogenous technological innovation is a big issue. But what I would like to say is that for sure makes our results to be of this huge magnitude. Even with technological innovation, I believe that, again, the contribution would be the same, because at the moment, I don't think that the technological innovation we have would reverse this result, okay? But for sure, the magnitude will be lower. But the point is also that, I mean, I could include endogenous technological innovation, but the point is also population dynamics should be considered. And yeah, I've been working also on how to to population dynamics in terms of fertility and mortality. But now what I do have in mind is not anymore something like this, but it's more these dynamics, the way in which people will move would be very important in order to decide which areas of the world are indeed vulnerable. And imagine that technological innovation, besides being endogenous, it's not strong enough. Then we need other type of policies in order to lower the effect of climate damages. That's more or less but you are right, of course.
That was my second comment, was the instead of, I think your research and your paper argues that instead of having country or even larger regional climate goals or climate goals, it should be more maybe very strictly regionalized to urban areas. And those are going to look very different based, let's say Shanghai versus New York. So I thought that was the really nice contribution that your research shows.
Yeah, and you're, I mean, perfectly right. That's my main point, because since still global climate change is there, and the effect of global climate change, I'm not against global agreements, but I believe that maybe the debate on mitigation and adaptation policies could be more accepted by people at the moment if the type of intervention are more at the local level. And even from my perspective, I really can tell you that in Milan, you cannot live during the summer, okay? Or you have air conditioning, or it's not really possible. And this is an advanced economy with all the privilege and benefit that we can imagine, but still probably a more localized climate policies could be more effective, and maybe people could see the results even faster, okay? So maybe that could be one of the keys in order to keep on with the energy transition, let's say, and climate policies.
Absolutely. Any other questions or comments? Make sure I'm not missing anybody. All right. I don't see any. So do you have any last comments you'd like to make?
Well, I think I would just want to thank you all for attending this seminar today. It was very nice for me to present my research to a different audience, and I really appreciated the questions. And yeah, that's it. I will participate as well to the future seminars organized by the society for sure.
Thank you. And before we finalize everything, I just want to show everybody our next seminar. That was a unexpected but excellent segue. So our next seminar will be February 14th at noon Eastern Time by former President Valerie Luzatis from SUNY ESF. And her talk will be Heart Forward Science, Engaging Imagination, Intuition, and Intellect for Solutions to Confounding Science and Societal Problems. It's a new line of research, and we're looking forward to that. So with that, I just want to thank Veronica once again very much for an excellent presentation. Very interesting research. You can find her papers online very easily, and ecological economics was one of the ones presented today, and I really encourage you to look at those. And once again, thank you very much, and have a nice weekend, everybody.
Thank
Thank
you
you.
all. Bye.
Bye.